Projectile motion is the motion of an object thrown or projected into the air, subject to only the acceleration of gravity. We have already considered the motion of falling objects, which is the simple one-dimensional type of projectile motion in which there is no horizontal movement. In this section, we consider two-dimensional projectile motion with air resistance negligible. The most important fact to remember when considering the projectile motion is that motions along perpendicular axes are independent and thus can be analyzed separately. The key is to break the motion into two motions, one along the horizontal axis and the other along the vertical axis. Because acceleration due to gravity is vertical, there will be no acceleration along the horizontal axis when air resistance is negligible. We may notice that the only common variable between the horizontal and vertical motions is the time t. After we solve for the unknowns in the two separate motions, we recombine the two motions to find the total displacement s and the velocity v. This picture shows how the x and y motions are recombined to give the total velocity at any given point on the trajectory. Let's look at this example together. Please pause the video here and read the questions. From the description, we know that the shell explodes just as it reaches its highest point above the ground. The highest point in any trajectory is reached when Vy equals to 0. Considering the motion in the vertical direction, the known quantities are initial velocity, final velocity, which is 0, acceleration minus g, and we can set the initial position to be 0. And the quantity to be determined is the final position, which is the height of the highest point. Since the time is unknown, we use this equation to find the height. We set the initial position y0 to be 0, and Vy is 0 for the highest point where the shell explodes. The equation simplifies, and we can get y equals to V0y squared over 2g. One tricky part here is that although we have known the initial velocity of the shell, which is V0, since V0 is not vertical, we need to find its vertical part. We have V0y equals to V0 times sine theta, and after plugging all the numbers, we get the final result, y equals to 233 meters. In question B, it asks about the time between the launch of the shell and the explosion. Now, the known quantities are the initial velocity, final velocity, acceleration, initial position, and also the final position because we have solved for it in part A. We need to determine the time, and it is possible to use this equation. However, there is a better way to do it, which is to use the equation y equals to y0 plus the average velocity, which is 1/2 v0y plus vy times the t, because we know all the initial and final velocities and the positions. After plugging all the numbers, we can get the time equals to 6.90 seconds. In part C, it asks the horizontal displacement of the shell when it explodes. Because air resistance is negligible, the horizontal velocity is constant. We have the horizontal displacement x equals to horizontal velocity times the time solved in part B. Since the horizontal velocity is the x component of the initial velocity, plug in all the numbers. We have x equals to 125 meters. In the last example, we see the maximum height we found for any projectile motion when air resistance is negligible is h equals to v0y squared over 2g. This equation defines the maximum height of a projectile and depends only on the vertical component of the initial velocity. We also see the horizontal displacement between the launch and the highest point is x equals to vxt equals to v0 squared sine 2 theta 0 over 2g. Due to symmetry, the range r of the projectile on level ground, for which air resistance is negligible, is given by r equals to 2x equals to v0 squared sine 2 theta 0 over g. Let's look at this example. Please pause the video here to read the questions. If we define the right direction to be the positive x direction and the upward to be the positive y direction, we have the ball doing a free fall in the vertical direction, while in the x-axis direction it has a constant velocity v0. For the question A, we use this equation to calculate the time t. The initial position y0 equals to 60.0 meters. The final position y equals to 0 because the ball lands on the ground. v0y is 0 because the ball is thrown horizontally. Plugging all the numbers, we have t equals to 3.50 seconds. For question B, since we know the ball travels 100.0 meters during that 3.50 seconds, the initial horizontal component of the velocity v0 is 28.6 meters per second. For question C, the vertical component of the velocity just before the ball hits the ground can be calculated as Vy equals to minus gt, which is minus 34.3 meters per second. For the question D, since we already have the horizontal and vertical component of the final velocity, we can get the magnitude V equals to 44.7 meters per second, and the theta equals to minus 50.2 degrees. If a person rows a boat across the rapidly flowing river and tries to head directly for the other shore, the boat instead moves diagonally relative to the shore, because the river carries the boat downstream. Similarly, if a small airplane flies overhead in a strong crosswind, the plane is not moving in the direction in which it is pointed, because the movement of the air relative to the ground carries it sideways. The rules of vector addition also applies to the addition of velocities. Let's see this example. Because V total is the velocity sum of Vw, which is velocity of wind, and Vp, which is velocity of the plane. If we define the east direction to be the positive x direction and the north direction to be positive y direction, in the x direction we have V total x equals to Vwx, since the plane only has vertical component of velocity. In the y direction, we have V total y equals to Vwy plus Vp. Plug in all the numbers. We have the x component of the wind velocity is minus 13.0 meters per second. The y component of the wind velocity is minus 9.29 meters per second. So the total magnitude of the wind velocity is 16.0 meters per second, and the direction angle theta is 35.6 degrees. When adding velocities, we have been careful to specify that the velocity is relative to some reference frame. These velocities are called relative velocities. For example, the velocity of an airplane relative to an air mass is different from its velocity relative to the ground. Both are quite different from the velocity of an airplane relative to its passengers, which should be close to zero. Relative velocities are one aspect of relativity. Talking about relativity, we may immediately think about Einstein and his famous theory of relativity. Actually, what Einstein developed is the modern theory of relativity, while Galileo and Isaac Newton had successfully described the classical relativity, which applies to the situation where speeds are less than about 1% of the speed of light. Let's look at this example. The motion of a coin dropped inside an airplane can be viewed differently by two different observers. When measured relative to the plane, the coin falls straight down like a free fall. We define the upward direction as the positive direction, and the acceleration is minus g. We use this equation to find out the final velocity, since we don't know the time. We choose the negative root value because we know that the velocity is directly downward. We measured relative to the Earth. Since the vertical motion is independent of horizontal motion, and the initial vertical velocity relative to the ground is 0. The final vertical velocity for the coin relative to the ground is also Vy equals to minus 5.42 meters per second. And the final horizontal velocity are the same as the horizontal velocity of the airplane, which is Vx equals to 260 meters per second. Combining both x and y components, we get the magnitude of the final velocity v to be 260.06 meters per second, which is just 260 meters per second if we consider the significant figures, and the direction angle theta to be minus 1.19 degrees. This shows that an observer on the ground sees the coin move almost horizontally.